Right, Mr. Newton, now you're keeping your hands, feet and objects to yourself, like I've read somewhere you should be. I'm going to show you a method that makes the numbers much more manageable and so easier to work out the mean and standard deviation, and that's called coding.
Right, okay, what do you mean by coding then?
Right, well, each of these pieces of data here, these are what we're thinking of as our x values.
Right, x. Okay, right, cool. So they're my x values. Cool.
And we've been given a formula that will make these numbers smaller, and this is what we mean by coding. So the first thing it's telling us to do is take away 100 from each x value.
Right, I want to do that. 86, 100, I can do that, yeah, it's easy. 10, 20, 20 again, 50, 60, 80. Well, they look much better already.
Yeah, much smaller. But we're going to make them even smaller. So the next thing it's telling us to do is to divide by 10.
Okay, and that...
And that's telling us that's what we're going to call y.
Okay, so like my y values, I've got this. Okay, so divide by 10. I can do that. I don't even calculate actually.
It's a good job, isn't it?
Well, I broke that last one.
Right, well now our data's much smaller, we can find the mean and standard deviation for this data.
Right, okay. Well, okay, so instead of sum of x, I'm going to use sum of y.
That's right, yeah.
Okay, so if I do mean, so I call it y bar.
Exactly.
I can say that's sum of y over n, number of items. Okay, so let's work out sum of y. I can do that. Sum of y. I could do this without a calculator. That's 5, that's another 5, that's 10, 16, 24. Is that right to say?
Spot on.
Okay, cool. Right, so then standard deviation, what's that? It's the mean of the squares, so y squared. I'll tell you what this is in a minute, minus the square of the mean. I've just worked that out, okay, right. And that's variance, so then I have to square root to get standard deviation. Okay.
That's right.
I'm going to need sum of y squared, and I'll do a y squared thing. I can do that as well. I might need another calculator in a bit, so hopefully this one works. I'll probably the other one. Okay, so sum of y squared, I'll put this up here like it's all my bits that I need. So that's 100, 125, and then I've got another 9, so it's 134.
I think so, yes.
Hopefully it is. Right, okay, so now I'll just plug it in. So I've got the mean, y bar, and that's sum of y over n, number of things, and there's 6 of them, yeah, okay, cool. So that's 24 over 6. Okay, so that equals 4. Y bar, put a little box around there. And then sigma squared, I'm going to have to use calculator for this, but let's put them in. So we've got the mean of squares, so that's 134 over n, which is 6. Take away this one, well it's mean squared, so I can actually just put the 4 in, that's cheating a bit, but that's what sum of y over n is. So I can work out my sigma squared. I'm going to type it in. Right, 134 divided by 6. And then I want to take off 4 squared, well that's 16. Okay. So 19 over 3. I'm just going to leave it like that so I don't lose any accuracy. No, square root that one there. Root 57 over 3. Well, I want to write down what it is as a decimal for a while. So, and then I'll just round it. 3c pigs, is that about right?
I think that'll be okay.
Okay. 5, 2. And I'll say 3c pigs. Okay, so I think I'm there. So is that... Well, if this is y, I'm going to put a little y on the bottom of this so that this is like the variance and standard deviation of the y values. Is that the same answer then for the x values?
Well, if we look at this, would it make sense for the mean of this data to be 4?
No.
And would it make sense for the standard deviation to be 2.52?
Like the spread of it?
Yeah.
No, I don't
So
think
we need to do something to our data to find the mean and standard deviation for our original things. Now you're in luck. Mr. Barker has an excellent method for explaining this.
Brilliant.
Dot, dash, dot, 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 dot. We don't need this, chaps. Alright, Mr. Newton. So, you can see here, I've got my data all in a line. So this represents the data we're working with. And it's all spread out evenly across the line.
What's that green cross, Mr. Barker?
The green cross represents my mean.
Okay.
Now, generally, when we're coding, we're working off a system where we say y, our coded data, equals x, our original data value, minus a, all divided by some value b. So this is generally the formula we use for coding data. Now, if we take this bit by bit, when we take away a from our data set, that has the effect of moving everything down by a value of a. We're taking away a from each member of the data set. So we can see I've filled out most of them. All I've got left, I've got to put my mean in, so that's moved down there as well. And I've got one more piece of value from my data. So the whole data has moved down. We can see it's just as spread out, but it's just moved along the number line. So taking away a doesn't affect the spread of the data or any measure of variance, but it does affect where the mean is.
So you'd say that subtracting a does affect the mean, but does not affect the standard deviation. Is that right?
Very good, Dr. Young. Are you taking this down, Mr. Newton?
I'm getting it down on my note sheet, sir.
Oh, that's beautiful. It's starting to look Da Vinci-esque.
Thank you, sir.
Right, so that's the first bit dealt with. We've taken away a. Now, when we divide by b, we're dividing every single value in our data set. Just like when you divided by 10, you divided every single value of x by 10. And obviously when we're dividing, that's going to have the effect of scrunching everything up, squashing it together. So the spread of the data is now much, much thinner than it was before. And obviously because every value has been divided by b, so is the mean. So the mean's shrunk again. So the spread is narrower and the mean has changed when we've divided by b.
So dividing by b not only affects the mean, but also the standard deviation.
Boom, you got it.
Okay, so in the data we had, we used this coding, and I got that as the mean, that as the standard deviation. Cool. So let's do what Mr. Barker said then. So if I look at this coding thing, if I want to do the mean, so I've got y bar, that's my mean if I have the y data. Well, I think if we start with the x values, the x bar, the x mean, whatever you want to call it, we're taking off 100, which is going to move it all down. Okay, so that's affecting the mean. Take off 100 affects the mean, so I need that in there. Dividing, so that also affects the mean. Both of them affect the mean. Brilliant, okay. All I need to do now then, I guess, is just put my value in for y bar, which is 4, and I can solve this equation. Okay. And it's nice to do numbers actually. I times by 10 to get 40, add 100, so x bar is 140. Okay, brilliant. Well, that seems more realistic. Let's have a look at the standard deviation then. So if I use this same formula here, I think what Mr. Barker was saying was that if you're just taking off 100 off, that's just not going to affect any spread, it's just moving everything down. So I think standard deviation of x won't be affected by that taking 100, so I'm going to forget that set, I'm going to get rid of it. Okay? And then I'm still going to have to divide by 10 because that's scrunched everything up. Okay, so that's going to be there. Now this time I've got a slightly more tricky number, and actually I'm going to look back at my working. I put it a bit more accurate here, it's like 2.5166, so I might use that in my working. So let's make sure I can see that. So this is my standard deviation for y, 2.5166 dot 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 dot. That was standard deviation of x divided by 10. Well, I can times by 10 and I'll get 25.166 dot dot dot. Standard deviation of x. Standard deviation of x is more like 25.2, and that's the 3 sig fix. Okay, I'm going to check that looks about reasonable with the data. So yeah, that seems sensible. These values here, 140 seems some kind of measure for the location somewhere near the centre of the data, and spread out by 25.2. That seems like a reasonable looking at those numbers. Okay, brilliant. Wonder what would happen if you had maybe some group data.
Right, we're going to have a look at this example where we've got some grouped data this time. Now it doesn't say this in the question, but what we're going to do is we're going to code this data using the following coding. Now because we've got group data, we're going to have to take the midpoint L for these groups. And what we're going to do is we're going to say that y is equal to L, and we're going to subtract 7.5 and divide by 5. Now in the exam you'll always be given the coding. So if we want to find the mean of this data, we use the midpoint just like we've seen previously. So we want one extra column on our table, that's the midpoint. And then we want to then code that data. So we need another column that is going to be the coded data. So that's y equals L minus 7.5 over 5. And then here I've put the formulas for the mean and the standard deviation. So in the formulas for standard deviation, remember we need to square the data. So what we're going to do is we're going to square our coded data. So we're going to need to work out y squared, and then we need the frequency times each piece of data, so that's f of y, and we also need the frequency times our squared piece of data, so f of y times y squared. Right, well let's fill in this first row together. So our midpoint between 0 and 5 is 2.5. So then we apply the coding to it. So if we take away 7.5 from that, that will be minus 5. And divide by 5 gives us minus 1. But then this column is what we get when we square this. Well, minus 1 squared is 1. This one is our frequency times our coded data. So 4 times minus 1 gives us minus 4. And the last column is our frequency times our coded data squared. So 4 times 1, which is 4. So what you should do now is pause the video and have a go at filling in the rest of that table. Right, here is the filled in table. So I suggest what you do is you pause it again, check that you agree with all those calculations. You'll notice that I've filled in the totals at the bottom of f times y squared, f times y, and the total frequency. And I've summarised these at the side. So the total frequency is the sum of f, which is 27. The sum of f times y is 16.5, and the sum of f times y squared is 149.25. Pause the video and check you agree with those. Right, so let's go on to finding the mean and standard deviation for our coded data. So remember, our coded data is denoted y. So we're going to use our formula for the mean. So that means that y bar is equal to the sum f times y over the sum of f. Well, that's 16.5 over 27. And I go to the calculator. So 16.5 divided by 27, and that gives us 0.61 recurring. Right, let's do the standard deviation of y now, which is sigma, and put a y there to denote the standard deviation of our coded data. And that's going to be the square root of the sum of f times y squared over the sum of f minus the sum of f times y over the sum of f all squared. Well, that is just the square root of 149.25 over 27 minus 16.5 over 27 squared. And you go to the calculator and you type that in. And make sure you're accurate with this. And it should come out as 2.27. It's 2 decimal places. Now, It's very tempting to stop there when you are doing these questions. But this is the mean and the standard deviation for the coded data. We need to work backwards to find out what the mean and standard deviation for our original data for L. So remember what Mr. Barker was talking about. Coding, when we code, subtracting and dividing both affect the mean. So if we want to take our coding and we've got y bar is equal to L bar minus 7.5 over 5. Well, we've just worked out this is 0.61 recurring. So we're going to times by 5 and add 7.5. So 0.61 recurring times by 5, add 7.5. Should give us an answer of 10.5 recurring. Okay. Right, on the other hand, only the multiplying or dividing by 5 affects the standard deviation, because when we move our data by subtracting, that doesn't change the spread. So we've got that standard deviation of y is equal to standard deviation of L, not x, over 5. Well, we've just worked out this is 2.27. So we times up by 5, and so the standard deviation of L is 2.27 times 5, which is 11.35. It's 2 decimal places.